So what I'd like to do is talk first about the idea of categorification. So let me borrow a term from my colleague Dan Fried and talk about category number as a loose measure of the amount of abstraction that is involved in a particular mathematical idea, mathematical theorem, mathematical construction. So category number 0 refers to the most concrete type of mathematics. So the mathematical objects that you would be interested in at this level are things like numbers. And the kinds of theorems that I would call category number 0 theorems are theorems that are statements about numbers. Like a typical theorem would say that two numbers are equal to one another. So saying that that is category number 0 is not to say that it can't be a very interesting or deep statement. Many of the most interesting statements in mathematics are theorems of the form two numbers are equal to each other. It's just saying that this is a statement which has a very concrete meaning. So let me distinguish that from category number 1, where the objects of interest are not concrete things like numbers, but there's slightly more abstract things like mathematical structures. So there's all types of structures that we study in mathematics. Sets, which you might think of as having no structure at all. Things like groups, vector spaces, etc. And the kind of statements that you're interested in at this level are slightly different. A typical theorem would not be that two numbers are equal to each other, but you might want to say that two structures are the same. And here you would say not that they are equal, but that they're isomorphic. And the way that you give proofs of theorems at this level have a little bit of a different character. If you want to prove that two mathematical structures are the same, it's not a yes-no question. It's typically something that you prove by providing a construction of an isomorphism between two groups or two vector spaces or something like that. So I want to talk about going one step higher. Category number 2, the objects of interest are not individual mathematical structures, but categories, meaning classes of mathematical structures. And the typical theorem that you would consider at this level is a theorem of the form two categories are equivalent. So I want to emphasize that if you're not familiar with the idea of a category, well, you might still be familiar with mathematics that happens at this level. So for example, when we teach our students linear algebra, we typically first teach them linear algebra. It's a subject which is about matrices, which are these grids of numbers. We teach them how to multiply matrices and do all sorts of calculations with them. And then later we teach them a more abstract point of view. Linear algebra is about vector spaces and linear transformations and things like that. And hopefully we teach them that actually these two languages are equivalent. There's just two ways of describing the same underlying structure. So that's an example of an equivalence of categories. And so typical theorems at this level are theorems that tell you that there are two different ways of looking at a same mathematical structure, or there's two different mathematical structures that somehow are essentially the same. So I'm going to talk in this lecture about the idea of categorification, which is a term for taking some statement that you're interested in, which happens at one of these levels, and then studying a related statement that happens at a higher level. So rather than give you some simple examples to show you what I mean, I think I just want to take this entire lecture and devote it to one extended example. And the example that I want to start with is the Fourier transform. So let me remind you what the Fourier transform is. If you start with a function f from the real numbers to the complex numbers, then you can associate to it its Fourier transform which is given by the integral of f of x e to the 2 pi I xy dx. So the Fourier transform is a construction. It takes one function of a single real variable and produces another function of a single real variable. And this is a construction which I would say happens at category level 0. It's about very concrete objects. A function is not just a number, but it's a collection of numbers. It's a very sort of concrete mathematical object, and this is a concrete construction which takes one such object to another one. Now, one of the reasons that the Fourier transform is useful is that under appropriate hypotheses, f and f hat are equivalent pieces of data. You can translate questions about f to questions about f hat, and often the translation procedure makes those questions much easier to answer. So let me describe a sort of proto-theorem about the Fourier transform. Is that the Fourier transform gives you a bijection from functions from R to the complex numbers to functions from R to the complex numbers. So I'm calling this a proto-theorem because as it stands, well, if you interpret this literally, it's false. It's a proto-theorem because it's a sort of loose description. It's an informal statement of a class of theorems that you might want to prove. So there are various theorems that instantiate this proto-theorem. So for example, an actual theorem along these lines would be, well, you attach some precise meaning to what you mean by function. What kind of functions do you want to consider? Well, one of the nicest statements is to consider square integrable functions. Square integrable functions on R, isomorphic to square integrable functions on R via the construction that takes f to its Fourier transform. So this is now a statement that I would say is happening at category level 1. It's a statement that two structures are isomorphic to each other. In this case, it's the vector space of square integrable functions on R is isomorphic to itself via a particular construction.
It's still cheating because the element of L to R is not a function. No, this is serious. I mean,
might have moved you into another
it will not
structure.
be easy to find what indifferent.
So I don't want this talk to be about the details of instantiating the proto-theorems. So if you like, I'm about to switch to talking about the discrete Fourier transform and for finite groups, and then it's literally true. But I'm just going to talk at the level of proto-theorems. So this Fourier transform is some construction. It takes concrete things like functions, produces other concrete things like functions, and a category level 1 statement about it is that it's giving you an equivalence between those two types of data. And I think it is worth pointing out that, well, if you want to describe the construction, you don't have to worry too much about exactly what you mean by function, right? A function, you can take a sort of 18th century point of view. A function is something I know it when I see it. Here's a formula for it. But if you want to prove an example of a theorem of this type, then you have to say exactly what do you mean by a function. Or maybe it doesn't mean function at all. Maybe it doesn't quite mean function in the usual sense to make this statement about L2 spaces. But this is something which is typical, I think, of what happens when you move from one level to the next level. It forces you to think through questions like that. OK, so this Fourier transform is sort of a story which is happening between these levels 0 and 1. And I would like to talk about categorifying it. That is, finding analogous phenomena which happen at higher levels. So let me start by mentioning one of the properties that the Fourier transform has, which makes it so useful. So let's suppose that you have a function from the real numbers to the complex numbers. Then you can always, and you have some real number t, then you can always take your function f and translate it by t. So if t is a real number, let's define f sub t of x to be f of x plus t. So this is another function from the real numbers to the complex numbers, and you can contemplate its Fourier transform. And, well, you can just read off directly from this formula how that's going to be related to the Fourier transform of the original function f. This is the Fourier transform of f times something times some simple function that depends on y. So this is, in some sense, the defining property that the Fourier transform has. And one of the things that makes it so useful is that it converts the action of translation on functions from R to the complex numbers to the action of multiplication by some functions that we understand very well. Or another way of saying that is if you think of functions from the real numbers to the complex numbers, let me now specifically say I'm thinking of L2 functions. This is a representation of the group of real numbers. This group acts on L2 functions by translations via this procedure here. And that group of translations is an abelian group, and therefore you would expect that you ought to be able to, in some sense, simultaneously diagonalize all of these linear transformations. And this is, in some sense, what this Fourier transform does for you. It gives you some sort of something you can think of roughly as a basis for L2 functions on R, in which this translation action is just diagonalized for you. So this is something that you could contemplate doing for any group. If you have any group G, you can talk about functions on G. So, well, you could talk. And then you can study the action of G on that space of functions by translations. And you might try to simultaneously diagonalize all of those translation operations. So let me be a little more specific, specialized to the case where this works particularly nicely. So let's assume that G is compact and abelian. So some examples would be G a finite group, or G being the circle group. So those are particularly nice assumptions because, well, if you have the compactness of G guarantees you that any representation of G can be broken up as a direct sum of irreducible representations. And the commutativity of G guarantees you that all of the irreducible representations are one-dimensional. So any representation of G can be broken up into one-dimensional bits. And in particular, you can study what that does to the space of L2 functions on G itself. So let me introduce a notation. So G check is going to mean the dual group of G. So this is the collection of characters of G. So an element of G check is a function from G to the unit complex numbers. A function lambda which converts the multiplication in your group G to multiplication of complex numbers. So why is that an interesting thing from this point of view? Well, if you have any function, f, from g to the complex numbers, suppose that if you think of it as sitting inside this vector space of all functions on G, if it were a simultaneous eigenfunction for all of these translation operators, then it would have to be a scalar multiple of one of these characters lambda. In other words, if you knew, if for all elements G and G, you knew that there was a formula which said f of gh is f of h times some scalar that depends on G, then, well, what does this tell you? It tells you, first of all, that f of g is lambda of g up to a scalar times f of 0. So it's a scalar multiple of whatever this function lambda is. And secondly, as long as f is not 0, that'll tell you that this lambda has to be one of these characters. So the Fourier transform or Fourier series in a more abstract form or a more general form for a general group G says something like that the space of functions on G breaks up as a direct sum of one-dimensional representations which are indexed by this set of characters. In other words, every function on G can, in the suitable sense, be written as some linear combination of these characters. And writing a function as this linear combination, that's expanding a function in its Fourier series. Or at least that's what this means when the group G is S1, which is a perfectly respectable case to think about for everything that I'm going to say from now on. So, but this is something you can contemplate not just for the vector space of L2 functions on G. You can contemplate this for any representation of G. So suppose that G acts on a vector space V. Well, what I said earlier tells you these assumptions on G allow you to break V up into a direct sum of one-dimensional representations, each of which is characterized, can just be described by a character. So that decomposition is not quite canonical. For example, if your group G was trivial, it's like choosing a basis for V as a vector space. But what is canonical is what's called the isotypic decomposition. So in this situation where you have your group G acting on a vector space V, well, for each character, lambda, you can look at what I'll denote by V lambda, which is the set of the collection of those vectors such that for all G in your group, G on V is just a scalar multiple of V, where the scalar is given by lambda. So this is a subspace of the vector space V that you started with, and a sort of proto-theorem, well, is that V can be recovered as the sum of these subspaces V lambda. Or let me state this more precisely as less precisely, as a sort of proto-theorem that you can contemplate in this context, which is that the construction that takes a representation of G and assigns to it these subspaces gives you an equivalence between representations of G and families of vector spaces parametrized by G dual. So I want to think of this prototheorem as an analog of the previous prototheorem. So the previous prototheorem was about functions on G. It was telling you any function on G can be, well, I stated it earlier for R instead of a general group G, but it was telling you that any function could be written in some sense as a linear combination of characters. So this is a statement not about functions on G, but about representations of G. And it's saying that any representation can be written as some sort of combination of representations that we understand very well, which come from the characters of G. So I would like to think of this as analogous to the previous theorem. But it's not just analogous to the previous theorem, it's also closely related to the previous theorem. Because if you take this prototheorem and you wonder what happens when I apply this procedure to my favorite representation of G, like the representation of G on this space of functions, well, what pops out is the theory of the previous construction of the Fourier transform, or a Fourier series. Fourier series are what you get when you apply the isotypic decomposition to the space of L2 functions on G. So this prototheorem I would describe as a categorification of the previous one. This is a statement at a higher categorical level. The construction is one step more abstract than the previous construction. We're not taking functions to functions. Now we're taking mathematical structures. On one side, we have representations of G, vector spaces with some additional data. And on the other side, we have families of vector spaces indexed by the dual group. Again, essentially vector spaces with some additional structure. So that's a slightly more abstract setting. And the theorem, the prototheorem, is also at a more abstract level. It's not a theorem that two vector spaces are isomorphic. It's now a theorem that two categories are equivalent. So I would like, in the rest of the talk, to do this one more time. I would like to describe for you a theorem which is a categorification of this prototheorem. So in order to do that, I want to look at this right-hand side and think of it as analogous to something that we saw before. So I want to think of these objects, families of vector spaces parametrized by G check, as a kind of, analogous to functions on the group G dual. So I want to think of these as functions from G dual, well, not complex valued functions on G dual. We're not assigning numbers to every element of this group. Instead, we're assigning vector spaces to every element of this group. So functions from G dual into vector spaces. So let's say we had such a thing. It's just a collection of vector spaces indexed by G dual. And now, just like with functions, there's an action of G dual by translations. So if we had some other element mu in G dual, then we can take one of these families of vector spaces and just translate it by mu. So let me define mu of this. It should be another object of the same type. It's another collection of vector spaces indexed by the dual group. But now I'm just going to take each of these characters and multiply it by mu first. So this is just precisely analogous to earlier how we thought of the group G acting on complex valued functions by translations. So this construction, meaning the construction that I just described, gives you an action of G dual on, well, let's say the kind of mathematical objects that we're thinking about here. Families of vector spaces parametrized by G dual. So I want to think this is saying that these things here form a representation of G dual. But now it's a representation in a different sense. G dual is not acting on a vector space. Instead, it's acting on a category. It's acting on a class of mathematical structures whose individual members are like vector spaces, or they're like vector spaces with some additional bells and whistles attached. So this is something that you can contemplate more generally. Just like earlier, we started by thinking about the first representation that I mentioned in this talk was the regular representation. Any group G acts on the collection of complex valued functions on G. Well, this is kind of like the regular representation of G dual, but it's not a complex valued function that we're thinking about, but a vector space valued function that we're thinking about. So this is like the regular representation in, well, in this new context. But now, instead of thinking about the regular representation, let's think about an arbitrary representation. So more generally, one can consider representations of this group G dual on any category C. So if you don't know what a category is, what I'm talking about roughly is a category is something which is a collection of mathematical structures. And saying that we have a representation of G check on this category C means that we have a rule which, given any structure of the type that we're contemplating, any object of the category C, we can translate it by any element of G check to obtain a new structure of the same type. So I've now erased my formula for how you do this with vector spaces which are parametrized by G. But that's a typical example, and maybe one of the simplest. So I want to think of representations of G dual on categories as analogous to representations of G on vector spaces. It's a categorification of that idea. So if you have a group G which is acting on a vector space, there's all sorts of things that you can do to it. So one thing that you can do is look at the space of invariant vectors. So V superscript G is defined to be the collection of vectors in your vector space V such that GV is equal to V for every element of your group G. And this is a subspace of the vector space V. It's the largest subspace on which the group G is acting trivially. It's the subspace of invariant vectors. So this is one of the first things that you might ask. If someone gives you a representation of G, you might ask, all right, what are the invariant vectors? Are there any? So there's an analogous construction that you can do when you have a representation of a group on a category. So in this case, you can consider the invariant objects of C. So by analogy here, I'll denote the invariant objects by writing a superscript where that's the group that's acting. And what are these? Well, these should be objects of your category which are fixed by the action of this group. So you want each of these objects when you act by an element of your group to be carried back to itself. But now we're talking about categories. That's no longer a condition. It's a structure that you should contemplate. So objects of C together with an isomorphism of lambda C with C for all lambda in your group. So this isomorphism, let me denote it by alpha lambda. And these isomorphisms should themselves satisfy a condition. Sorry? Should be compatible with multiplication. So this is a definition. Let me not worry too much about spelling it out. But I want to emphasize something that's different between this construction here and the construction below that it's based on. So if you have a group acting on a vector space and you look at the invariant vectors, you make something simpler than your original representation. This V superscript G, it's a subspace of V, and it's something that you think of as being smaller and easier to understand. In this case, that doesn't necessarily happen. So let me give you an example. Let's suppose that you take C to be the category of vector spaces. And I want to let this group act on it, and I just want to take this to be the trivial action. Meaning if you have some element lambda, the way it acts on a vector space V is just by taking it back to the same vector space V without changing anything. So then what do you get when you apply this construction? Well, now you want to be talking about objects of your category. In this case, that means vector spaces, together with an isomorphism of lambda of your vector space with your vector space. So what we are considering here are vector spaces V together with plus isomorphisms alpha lambda of V. Well, here I said with lambda of V, or lambda of C. But I'm considering the trivial action where lambda doesn't do anything. So these are isomorphisms of V with itself, satisfying the condition that the formation of alpha is compatible with products. So what is this? Well, the data of a vector space V together with those isomorphisms, that's just what we mean when we, that's a representation of G check. So the category of vector spaces, that's something that we think of as very simple, something that we understand very well. And when we apply this construction of taking invariance to it, we get something which possibly we don't understand very well. We get the category of representations of G check, which we think of as more complicated than the category of vector spaces. So here we thought, well, the invariant vectors sit inside of V. In this case, well, there's a map from representations of G to vector spaces where you just take the underlying vector space and forget the action of G. But that's no longer something that you think of as behaving like an inclusion. It's something that, in some sense, forgets everything that's interesting. If I give you a representation of G, you're probably not so interested in what its underlying vector space looks like. After all, vector spaces, the only interesting question to ask about them is what dimension they have. What you're interested in is not in the vector space V, but in what these isomorphisms are. That's where the real meat of the representation lies. And one one avatar of that is that if you have a representation, you can often find many representations that have the same underlying vector space. If you have data like this, you can often find a new representation that has the same underlying vector space V, but with different isomorphisms, alpha lambda. So let me return for a moment to the general case, where we're talking about a category C, which has an action of the group G check. And let's suppose that I give you an invariant for this action. So what does that mean? Well, remember, that means that we have an object of the category C, and we have isomorphisms between it and all of its translates. So then you can try to form, let's try to modify this invariant object without changing the underlying object of C, only changing these isomorphisms. You can try to form a new object, let's call it C prime, inside the invariants, where I'm going to take the same underlying object of C, but instead of using the isomorphisms alpha lambda, I'm going to replace alpha lambda by alpha lambda times some scalar. And that scalar, well, I don't have to use the same scalar for all lambda. Maybe that scalar will depend on lambda. So question, when does this make sense? In other words, when does this construction, just multiplying all these isomorphisms by a scalar, give you a new element in this category of fixed points? Well, there's a condition that these alphas have to satisfy, which I wrote down over here. And that condition places a constraint on how these scalars should behave. And the answer is this makes sense whenever C lambda lambda prime is C lambda times C lambda prime. So for example, if C lambda was given by evaluating lambda on G for some element of your original group G. So what have I just described? Well, I've just described for you a construction which does the following. It takes as input categories C acted on by G dual. So this is like representations of G dual, but again, not on vector spaces, now on categories. And it produces, via the construction of taking C to the invariant part, produces for you a new category. But that new category has some additional structure. Given any object, you can rescale these isomorphisms to produce another one. You have one such construction for every element of your original group G. This produces categories acted on by the group G. And now let me state for you a sort of proto-theorem about this construction. So this construction, let's say, just say, is an equivalence. This construction is invertible. It's essentially its own inverse. You get a category acted on by G. If you sort of do the same thing, but taking G invariants, you can produce a category acted on by G dual. It's essentially the category that you started with. Once again, this is a proto-theorem. And in order to turn it into an actual theorem, I would have to be very specific about what kind of groups I'm thinking about, what kind of categories I'm thinking about, and so forth. But instead of doing that, I have 3 minutes left, according to my clock. I just want to emphasize the analogy that I sketched for you. I just want to bring out the sense in which the 3 constructions that I described for you, each one at a higher level of abstraction than the previous one, are in some sense the same, or they're all avatars of the same idea. So let me remind you, the first thing I talked about was the Fourier transform, or Fourier series, which took functions on G and identified them with functions on G check, or functions from G to the complex numbers, and related them to functions from G check to the complex numbers. And the second thing I talked about was the isotypic decomposition. Sorry, my chalk is. And here you were talking about representations of G on vector spaces. And on the other side, you had functions from G check into vector spaces. And this third, most abstract thing that I described, well, we were now still thinking about representations of G, but now on categories. And I'm saying that those are the same thing as representations of G check on categories. So first, I want to bring out an analogy between passage from this line to this line and passage from this line to this line. So on the right here, you're thinking about functions on G check. On top, you're thinking about complex valued functions. Here, you're thinking about vector space valued functions. On the other side, the replacement that matches with that is replacing thinking about functions with thinking about representations. Now, passage to this line is based on the same procedure. You replace thinking about functions from G check to vector spaces to actions of G check on categories. You're replacing functions by representations. And here, well, in some sense, you don't change anything. You were talking about representations before. You're still talking about representations. So there's a strong analogy between, first, these 3 statements, and also how you pass from each one to the next. And once again, these are not just related by analogy. They're related in a more precise way, is that you get each of the stories above by taking the story below and applying it in the simplest example. If you want the theory of Fourier series, well, you apply the isotypic decomposition to the representation given by the regular representation of G, the representation on L2 of G. If you want the theory of the isotypic decomposition, you apply this to the regular representation of G on categories, which matches on the other side with the representation of G check on acting trivially on the category of vector spaces. All right, I'm out of time, so I will stop there.
Curious to know what you would really call an action of a group on a category, because that's not so obvious. I mean, you have an element of the group and an object to associate with the object, but what are the axioms precisely because of the difference with equivalence and isomorphism?
Yeah, so one way to, so for every element of G, you associate equivalence of the category with itself.
Oh, an equivalence.
For every pair of elements, you give an isomorphism of the equivalence associated to G times H with the composition of the equivalences associated to G and H individually. And for and there's a diagram that needs to commute involving 3 tuples of elements.
And it stops there. I mean,
and it stops there, yes.
You don't have to go in detail.
Right.
it's like, on the face of it, the first and third lines look more similar than the middle one because the change happens first on the left and then on the right. Are there further? If you had an audience with higher category powers, could you?
Well, here, let me make these other lines look more analogous.
Okay.
Let me say it in a different way. So the isotypic decomposition describes a relationship functions from BG into vector spaces to functions from G check into vector spaces. And down here, we're relating functions from BG to categories to functions from BG check to categories. So G and G check have a G cross G check maps into C star by definition, and BG cross G check maps into the category of vector spaces as a sort of de-looping. There's given an element of G check, there's a corresponding one-dimensional representation of G, and BG cross BG check maps into categories.
Okay. So, but could you recall what is BG?
What's that?
You recall what is BG?
Recover.
What is
Recall
BG?
what's BG.
Oh, recall what BG is. Oh, so BG means BG is a space satisfying. Oh, this was an answer for mathematicians, not for.
Oh, the BG of topologies, you mean?
It's the BG of topology, yeah.
I
Word.
was wondering whether it was a category or whether it was a topological object.
Yeah. So maybe in this context, it would be easiest to think of it. I mean it as a category. It's the category with one object, and the automorphism group for that object is G.
Oh, okay.
So a functor from that BG into the category of vector spaces is a representation of G.
Okay, so that's
Yeah.
quite simple to define.